Alright, section 1.2, definitely one of the largest sections in the entirety of AP Precalculus. So I would think that there's no way we'd be covering this section of notes in only one class. This is probably going to be, in case this applies to you, like if the reason you're watching this video is you're missing a bunch of school or something, just so you know, this is probably going to be at least 2 days of class to cover all these notes. There's just a lot of it, even though a lot of this is really all not all that challenging, but let's dive right in. Hopefully a lot of it will seem like just review to you, like this first thing here about the definition of a relation. And by the way, this whole section is called function behavior, so we're going to obviously be talking about functions and including the definition of a function. We're reviewing that and stuff. But first, a relation is a set of ordered pairs. So anything that involves a relationship between like two variables, and really it just you could describe it as like just a set of ordered pairs. That's a relation. So here's an example of a relation. It's just a list of ordered pairs. Another way to show this relation is by a table. So you could kind of organize these ordered pairs obviously into a table. That should be no surprise there. That's not exactly earth-shattering to you. Far from it, I hope. And so 1, 3, 2, -2. So obviously behind that little box that goes, it would be -1. And then what number goes there? 3. And as always, feel free to pause the video as necessary to let something sink in, or for you to literally have enough time to copy everything down. You could also show a relation by a graph. Graphs show relations. So graphing all of these points, this should be almost like second nature to you. Graphing 1, 3, and then graphing 2, -2 as a point, and then the point -3, 5, and yada yada yada. I don't know. This should be something you've seen in the past at least once or twice. This concept of a mapping diagram. So you could also represent a relation with a mapping diagram where we put all the x coordinates over here and all the y coordinates over here, and we have these mapping arrows to show that like 1, the x coordinate of 1 maps to 3, so that's 1, 3, and the x coordinate of 2 maps to -2, so that's the ordered pair 2, -2, and yada yada yada. Or of course with an equation that involves two variables, normally x and y as those two variables. More definitions, more important definitions. Domain. You should hopefully remember what domain means. The domain of a relation or a function, little foreshadowing there, but the domain of a relation would be the set of all x values in that relation. So just if we separate the x values on their own, that's the domain, and if we separate all the y values of a relation, that's the range. So domain is the set of all x's, range set of all y's. So domain and range basically is x and y. Okay, now hopefully you remember somewhat what a function is. A function is a special relation in which each element of the domain is paired with one, and I guess there'd probably be like a with there, paired with, I need to add this in later, but a little bit of a typo there, I guess. each element of the domain is paired with one and only one element of the range. So every x only maps or only is paired with one and only one element of the range of the y. So for every x, there's exactly one y value. For every x, there's only one y value. And there's no x values that repeat. They map to one and only one y value, like I was saying. Question. Is the relation given on the front side a function? So recall this over here. So does this represent a function? And the answer is yes. And if you also want to write down, because there's no repeating x values, 1 only maps to 3. This x only maps to -2. Like if there was another ordered pair that would have said, like over here at the end, 2, 8, then you would have saw a repeat x value, meaning 2 maps to -2, and it also maps to 8, so that would have broke the rule, the only real rule about a function. That would have broke it. But this is a yes. But if we added the ordered pair, well, instead of 2, 8 in this little node here, we're adding, but same thing, we're adding 2, 4, then of course it would no longer be a function because you would have had 2, -2 as well as 2, 4 now. How about a mapping diagram? Can how do you tell whether a mapping diagram represents a function? So looking at this mapping diagram, that is a function, but looking at this mapping diagram, it is not a function. It's merely a relation. So this is also a relation, but this is a relation that is also a function. This is merely a relation because this element of the domain, this x value, is mapping to more than one y value. It's got 2 arrows coming off of it, so it's because of x sub 1, that x coordinate, that it is not a function. First example, does the formula, or equation, whatever, y equals x squared, define y as a function of x? And the key word in these directions is function. Basically, is this a function? Like for every x, is there only one y value? Or in other words, for every input, is there only one output? So this is kind of what I was saying, I guess. I'm assuming. Would there only ever be one output for any allowable input you could choose? I guess more on this word probably as we go, because sometimes, maybe I'll get into it a little bit right now. Sometimes you are allowed to plug in any number you want for x. Sometimes anything could be an input value, but sometimes that gets restricted a little bit based on what's going on in the equation. So that's why it says, like for every allowable input, could there ever potentially be more than one output for a particular input? And but the original question, is this a function? And it's yes. So since this is a function, think about it. No matter what you plug in for x, whether it's 2 or -2 or 5 or -7 or whatever you're plugging in for x, it's only ever going to spit out one possible answer, one possible output. So we can actually use the fancy function notation, f of x. Hopefully that sounds familiar back from like algebra 2 and stuff. But instead of writing your equation as y equals x squared, you can write it as f of x equals x squared because it is a function. Numerically, kind of what I was just saying. Numerically, it's about, throwing in a bunch of numbers, or just like imagining, plugging in all different kinds of numbers and literally seeing the numbers of, what output would you get, and seeing that there's only ever going to be one output for every input. Graphically, if we looked at the graph of this, could we tell just by looking at a graph? Try to remember. Can you tell by looking at a graph of a relation if it qualifies as a function? And the answer is yes, we can tell. So this picture of the three graphs, which is not a function. So, this one, look at this one, next, the second one, look at the third one. Are any of these not a function, and how can you tell? This one is not a function. And it kind of pertains to what maybe you remember as the vertical line test. It's probably going to be on the next page here. Yep. The vertical line test is, can you move a vertical line anywhere on the graph, left to right, and have it only hit the graph once? See how it's vertical line's only ever hitting the graph once? This vertical line, no matter where I put it, where I slide it, left to right, it's only ever hitting the graph in one spot. But this one, as soon as we get to like here, as we move left to right, it's obviously failing the vertical line test because it's hitting like exactly twice. But then from all of this, left to right, interval, it's hitting the graph in three places. Like here, this is an example of where it would prove to fail the vertical line test, which is written here. Moving on to this concept of change in tandem. This is definitely like a phrase, like a I don't know, a new phrase for AP Precalculus textbooks and curriculum, but it's really not that big of a thing. You can read that on your own. Example 3 shouldn't be too crazy. Rosina makes $16 per hour in her job. If there's a change in input kind of thing, what will be the change in her week's pay? And so if one variable changes, the other variable changes, and whatever. So if she makes 2 more hours, or she works 2 more hours per week, she will make 32 extra or more dollars. Agreement, some generic agreement. Unless we are dealing with a model like volume that necessitates a restricted domain, we will assume that the domain of a function defined by an algebraic expression is the same as the domain of the algebraic expression. I know that's like, what? The implied domain. For models, we will use a domain that fits the situation, the relevant domain. So, how can I explain this? This next example I get, sorry. I think it's going to be example B, if I remember correctly. So, so maybe I'll try to first explain it with example A. So this expression does not apply to anything, really. I guess it could potentially, but if I just give you this equation, which the expression over here is a big part of the entire equation. That's why, they're using the word expression only. So this is an expression that is like the right side of this entire equation, But anyway, so this expression doesn't really have any context. It's not like it's modeling some real world like formula, like volume or whatever, So you're just going to have to assume that like whatever the domain of this expression is the domain of the entire, thing. Like, what does it say here again? We will assume that the domain of a function is the same, as that expression. I mean, it's almost like too meta or too wordy. I don't know. So anyway, let's get down to it, I guess. More on this with example B. But to solve algebraically, okay? Think of it this way. To start, are we allowed to plug in whatever we want for x? In other words, is the domain going to be all real numbers? I mean, are we? Like, would we be literally allowed? Like, is there anything that would not make any sense? Like, the whole thing would just fall apart and blow up, or maybe give you an error on a calculator if you tried to plug in certain values for x? And the answer to this question is no. We are not allowed to plug in whatever we want for x. Because, remember, whatever you're taking the square root of has to be 0 or larger. In other words, you can't really take the square root of a negative number. Not without getting into imaginary land. A little bit of foreshadowing there, I guess, too. But if you remember from Algebra 2, the concept of like real versus imaginary, that's kind of what is going on here behind the scenes. We are not allowed to plug in whatever we want for x, because we in this context of domain, we are not allowed. Like, it's got to be real. So basically, this x plus 3 you can set up as being greater than or equal to 0, and when you get x by itself, just kind of isolate x. So we can, that means our domain is anything, so the only x values we're allowed to use is anything bigger than or equal to -3. Now, I believe what's here behind this next box is interval notation. I'm not going to get into that in this video, maybe so much, but I don't know, maybe in class we'll inevitably have to get into it, but this was kind of almost like a prerequisite thing, maybe a summer work potential thing. But the bracket, I'll get into a little bit maybe. The bracket means we are including -3, and we're going basically from -3 and including -3, and then everything after that to infinity. And we always put parentheses on infinities in what we call, again, interval notation. Supporting it graphically, more on that later, I guess, but you could definitely look at a graph and have like a graphical approach to figure out, like, what is the domain of this. Looking at the graph can be like a dead giveaway, and hopefully that makes sense. Looking at the graph, like everything that's actually graphed is from -3, I mean x value wise, right? From -3 and then forever to the right, because this graph keeps going and going and going. Forever to the right. Maybe it was example C about, maybe not example B about this, relevant and implied domain. Maybe there's an example C that will really show what that means, right? But so this one, the domain, think about it. You got this squared up here, so like right out of the gate you can see that, well, I guess we're not allowed to have any x's in our domain that are negative because of this numerator. But what would make the denominator, well, what is it about having a denominator that if you plug in a certain value for x, this whole thing would fall apart, get an error, what am I talking about there? What number are we literally not allowed to divide by? 0. So what would make, it's not about x equaling 0 necessarily. what would we plug in for x to make the entire denominator x minus 5 equal 0? And so that kind of inspires us to basically just write it out like this. Well, x minus 5 is literally not allowed to equal 0, and we could solve for x and basically figure out, thoroughly, algebraically, on paper, that x has to be greater than or equal to 0, but at the same time, it's not allowed to equal 5. So, hopefully this makes sense enough to you that this would be like the interval notation way to say that. And look at this, a bracket on 0, because we're allowed to include 0. We can plug in 0. I can plug in 0 for that x and for that x, and everything would be okay. But I put a parenthesis with the 5 because we're not allowed, we're going from 0 to 5, but we're not allowed to include 5. And then same thing over here, a parenthesis on 5, and then to infinity. So 0, 1, 2, 1.7, 0.8, 5.2, 6, 7.8, but these are intervals. And this symbol basically means the union. So it's like the combination or the union of that interval and that interval. It's basically saying literally everything greater than 0 and equal to 0 except 5. 5 is the only number literally from 0 to infinity, including 0. Not allowed. And then the graph, well, the graph shows it, how we can go from 0 and then off to the right forever to infinity, but we're not including 5. There's something called a vertical asymptote here. More on that later, like a vertical force field that the graph is never going to cross or whatever. But more on that probably later. And then here we go, finally. Example C. This is not just an equation with no context. This is representing the area of an equilateral triangle where S is the length of, one of the sides or all three sides. Seeing as it's equilateral. So with that in mind, if this equation, so here's where I kind of get a little more, I elaborate a little bit more on implied domain versus relevant domain. So if this equation had no context, if it was just a random equation like in a vacuum, we would be allowed to plug in anything we want for S. What's stopping us from plugging in anything? We're allowed to square any number we want. But since this is actually means something, like it's the length of a side of a triangle, the only relevant domain, you can't have a side that's negative 3 inches long, So if this function had no context, the expression in a vacuum would have a domain of all real numbers. And that is the symbol for all real numbers. It's like fancy shorthand for all real numbers. You could also say in interval notation, parenthesis, negative infinity, comma, positive infinity, parenthesis, and that would be like another way to write the set of all real numbers. So the implied domain is all real numbers, but again, this is an actual triangle. But the relevant domain here is, I guess you could have a triangle that has a, I don't know, you could even make it an argument, and I wouldn't argue with you too much that, wait, you can't have a triangle where the side length is 0, then the triangle wouldn't exist, but whatever. So 0 to infinity, and then, so graphically, this is just the whole equation in a vacuum, but the only, relevant part of the graph is, the right half, if we're talking about a triangle, and the area of it, the range. Remember the range, right? The range is all the y values. The set of all y values or the set of all outputs? So graphically, for this equation, you look at this, can you tell like what all, how you could represent all the y values on this graph? Analytically, numerically, it's kind of like they're similar here, where you just kind of look at this and go, is there any outputs that could never happen no matter what you input for x? So think about that. So this would be like an analytical, just kind of going with the equation. Numerically, where like you're just kind of like making a table, throwing in numbers and kind of analyzing it that way. Do you think like no matter what you plug in for, and by the way, you're not allowed to plug in 0 for x. That's why there seems to be like a vertical asymptote here, because you're not, there is no graph for when x equals 0. Like if I said find the point 0 comma something, you wouldn't be able to find it. There is no 0 comma something. There is no such a point on this graph, because we're not allowed to plug in 0 for x. So, but keeping that in mind, anything else we're allowed to plug in. But this entire 2 divided by something, is there any numbers that you could never, ever, ever end up equaling when you do 2 divided by something? And it turns out, I just got to write this down. I never wrote down the answer. But the range would be anything except 0. And look, notice, this is what we call a horizontal asymptote. How there doesn't appear to be any point for like, something comma 0. So I'm writing this with my mouse, so be kind to me here. So interval notation speak for every number, every real number that exists except 0. That would be interval notation, from negative infinity to 0 with a parenthesis on 0, union 0, not including 0, to infinity. Next we have the concept of increasing, decreasing. Okay. This would be the start, I believe, in section 1.2 of a series of concepts that are actually calculus concepts. So we're going to get a little, sneak peek, an introduction into some things that you can be doing in calculus. But the bare minimum basics, which is actually going to make this really, really easy, I hope, for you. So increasing and decreasing as an example. When I ask you, hey, take a look at this graph, and that's going to be the thing. We're going to be just looking at the graph. So it's almost like cheating, In calculus, you might not be looking at the graph. You might not be allowed to just look at the graph. There's going to be other ways that we learn to do this and answer this kind of thing in calculus. But in pre-calculus for right now, it's going to be, hey, literally just look at the graph and tell me, on what interval or on what intervals is this function increasing or going up as we head left to right, and on what intervals is this function decreasing as we go from left to right. So it's actually going to be like very, very easy. In calculus, you're going to take it up a notch, but here, so this is a function that's always increasing. On this function, it's constantly decreasing, and this is a good picture of a function that's constant. It's never going up, it's never going down as we head left to right. So this one is going to be decreasing, but when it gets to here, it'll be constant until it gets to this x value, and then it becomes increasing and it goes up. So we would say that as the interval for decreasing from negative infinity to negative 2. And these are x values in these intervals, okay? They're x values. And notice how there's a bracket here. That is something that, I don't know if controversial is the right word, but, if you verbatim go by the definition in our AP Precalculus textbook, which I think we're going to see the definitions here in a moment. A bracket is what's appropriate here, so including negative 2. So at negative 2, you can say that it's still decreasing, I guess. And it's constant, and look, brackets again. So at negative 2, you can say that it's, I know it's weird, you can say it's decreasing at negative 2, but it's also constant at negative 2. Certainly anywhere in between, it's constant. But again, it's really going to boil down to the literal words in the definition of decreasing, constant, and increasing. And then from positive 2 off to infinity, from 2 and then as we head off to the right forever, apparently, it's increasing. For this one, always feel free to pause the video if you want to kind of think about this first and predict what I'm going to be showing here. But so for this parabola, it's decreasing from negative infinity to 0. It's not constant anywhere. And again, this is going to be based on the literal definition, kind of following that verbiage religiously. But nowhere is this constant. And it's increasing from 0 to positive infinity. So here's the verbiage. And let's see, without dragging this out too much, I would have you, if you care about really understanding this deeply, I would probably highlight the word 2 points. Okay? A function is increasing on an interval if for any 2 points in the interval a positive change in x results in I guess maybe also highlight that word. It's pretty important to this definition of increasing. There's a positive change in y, like it's going up. So as we go left to right, as we head to the right, we're heading up. And this might be the most important word as far as you understanding why there's a bracket in a lot of these intervals rather than a parenthesis. 2, for any 2 points. So again, for any 2 points, and then same thing, this is what the thing with the parabola. A function is constant on an interval if for any 2 points in the interval there is 0 change, like it's flat. Moving on. Just more examples, right, of increasing, decrease. Again, in calculus, I don't know why I want to hammer down this point here, but in calculus, this could potentially be a tougher question to answer. You might need fancier tricks that you'll learn in calculus. But in pre-calculus, it's like, go to Desmos, go to your graphing calculator, and just look at the graph. And hopefully, it becomes a very, very, very easy question to answer, even if you have to end up approximating. On Desmos, it's a lot easier not to approximate or get these numbers correct. But like on your graphing calculator, even if it means like zooming in on a spot and going like, what's that x coordinate there, and needing to like approximate it. Whatever, like you're just going to be like looking at the graph. So I think this is just like a Desmos pic here, screenshot. So looking at this, I mean, again, this is what I was just saying. On Desmos, this exact spot, like spots like this, get highlighted automatically, or you could like click on a point or something. On your TI graphing calculator, it might not be so obvious, and you might need to like zoom in a bunch of times to realize like, oh, it looks like we are decreasing until x becomes exactly -2. Like not approximately -2 or negative 1.99, I don't know, but exactly -2. So what would go here, a bracket or a parenthesis? Bracket. And then it's increasing from -2 to infinity as we go left to right. Remember, these are x values. This next example, so again, probably better looking graph on Desmos than your TI graphing calculator. If you know what you're looking at here, you can see that there is a vertical asymptote here, and there's a vertical asymptote here, which makes sense because if you look at this equation and how, man, are we allowed to let x equal anything we want? No. Looking at this equation, it's pretty, and then looking at the graph at the same time, you go like, oh yeah, we would literally not be allowed to plug in -1 for x. There is no -1 comma anything for a point, and there's no +1 comma anything, because we would not be allowed to plug in 1. So as far as the increasing, decreasing stuff, here's what that means. This graph is increasing, it's heading up on this piece of the graph, but also this piece of the graph right there, like that left half of this upside down U-shaped thing. And this vertical asymptote thing, okay, we're not hitting -1. Like negative infinity going this way, but then we're never actually going to include -1. We're going to get as close as we want, like infinitely close. That's what these vertical asymptotes are all about. So we actually put a parenthesis on that -1 because we're not including it. We're never actually touching -1, and that's not a part of this graph, like this piece of the graph. Same thing with the -1 over here. But look, we're hitting this. Like this 0 is included, so that gets a bracket. So try to, go over this again if you need to, review it, and just try to understand why we're using parentheses here and a bracket there. Similarly with decreasing, it looks like we are decreasing from 0 to 1, but we're never actually going to hit 1. So that's why we have a bracket here, but a parenthesis here. And then this whole part of the graph is also decreasing. But again, we're not including 1, so it's from parentheses. Okay. Similarly, this is also, people, this is also in the same light I was talking about calculus versus precalculus. This is a big topic in calculus, but for precalculus, hopefully it becomes a whole lot easier of a thing, because it's really, again, it's going to boil down to just looking at the graph and, dumbing it down that way, just understanding what this even means as a concept. And here's what it means. So I'll let you write that, give you a second just to write all that stuff down. So concave up basically means as we curve upward, like the letter U, and right now your generic definition of concave down means that we're curving downward like an upside down U. So this, as you can see, is curving up. But even this, even though it's decreasing, you can kind of see how the curve is kind of facing up, kind of like the letter U, you know. And this would be concave down. And a point of inflection is where we're changing concavity, either from concave down to concave up, or concave up to concave down, kind of like here. So hopefully that makes sense, that we're like kind of concave down, like on this whole piece right here is concave down, it's curving down, but at this moment we kind of start to curve the other way. So that would be like a point of inflection. Again, like I just said, I mean, to answer these questions, we're literally just going to be looking at the graph, which is not all you'll be doing in calculus, I promise you. You'll be learning fancier, more in-depth ways to do it, more analytically. But graphically here makes your life very, very, very easy, or a lot easier than how you'd be doing it in calculus. So concave down, is there any, where do you think it's concave down? And I know this is not a very well labeled, but I think it's still obvious that from negative infinity to 0, and look, a parenthesis on 0. So that's going to be the difference in another kind of subtle difference in these definitions, the devil's in the details. A parenthesis now for an interval of concavity, which is like right here. So from negative infinity to 0, we're concave down, and then we are concave up from 0 to infinity. And the point of inflection, as best you can tell on this just kind of basic, graph, would be 0, 0. Okay? And in other words, at x equals 0. So in calculus, it's very common just to say like the x coordinate for your point of inflection, but obviously the entire xy ordered pair is 0, 0. Boundedness, not a big thing in calculus, to be honest. Also very easy in pre-calculus, and all we're going to be doing really is looking at the graph. So here's just a bunch of examples to kind of give you the gist of it. Because this is going up forever, and here, and also there, and here it's going down forever and down. I mean, so it's not bounded. Hopefully you get the wrap your brain around what this whole bounded word means. But this is an example of a graph that's not bounded above, and it's not bounded below. This one though, obviously this graph would keep going up and up. So it's not bounded above, but there's like a low point. So it is bounded below. It's bounded below by like kind of that value. But this is an example of bounded above but not bounded below. And if it's bounded above and below, like this one, this is about as high as it goes, and then this is about as low as it goes. If it's both above and below, then you just say it's bounded. And here's the worded definitions of all those things. Pause the video and go back, or pause it if you need more time to write all that stuff down. But again, checking boundedness, just a matter of like looking at the graph, Desmos.com, TI graphing calculator. So obviously looking at this graph, you could say it's bounded below. This graph, again, just throwing it into Desmos or whatever. And hopefully you can tell just by looking at this graph that it is both bounded above and below, so you just say bounded. Moving on. This is a big thing in early on in calculus, for sure. But again, the third thing in this lesson that it'll be like a little more in depth, a little fancier in calculus, but for right now in pre-calculus, we're just gonna look at the graph. And because we're just gonna look at the graph, this should become a really, really easy thing to do. But some vocabulary here for maxes and mins, and you learned about this kind of thing when you were doing parabolas in Algebra 2, the concept of a maximum value and a minimum value. But here in pre-calculus and calculus, we can use the word local. A local maximum greater or equal to all on some open interval, or like in its general area. More on this in examples. Like, it's easier to show you in examples and pictures, but or so I mean, for right now, you could have a local maximum. Like, you could have a bunch of local maximums. You might also have an absolute maximum. Again, more on that with the pictures. And then the same kind of thing for minimums. You could have like local minimums. You could also potentially have like an absolute overall minimum. And then just more verbiage and terminology. Local mins and local maxes, you could also call a relative max or a relative min. It's just like another word for the same thing. Absolute mins and absolute maxes you can also call global. In my experience, that's a very rare word to use. Like, I mean, it's almost like that's news to me, that an absolute min or an absolute max could also be called a global min or a global max. This I'm much more familiar with in all my experience as a high schooler myself and a college student and as a calculus teacher for a very long time. Local mins and local maxes, relative mins. This is a pretty good word to use because maybe that makes sense to you how, well, we have a spot that's like, it's a min, but it's like relative just to like its little area, its little section of the graph. But let's see this in action. Once again, just going to look at the graph to do this. It's almost like cheating. So look, do we have any local minimums? Yeah. This is a local minimum. Technically, this is also a local minimum, but wouldn't this also be like the absolute min? Because no point on the entire graph is lower than that point. Okay? But let's see. Now that I'm looking at what I have here, I'm looking back at the directions, and what I'm thinking here is the directions are literally only asking for local maxes and mins. They're not even asking you to identify if there's any absolute mins or absolute maxes and to identify them if there are. But let's see, so negative 24, so that'd be like this point. So that would be the minimum value, and it's at that. And you could tell this on Desmos, or if you zoom in enough on your graphing calculator, if you were to use that. But if the directions were asking you to also identify any absolute minimums or absolute maximums, this would also be an absolute minimum. Are there any local maximums? Yeah, right there. This is a maximum, but just like in this general area, just like this, and that's the only one. Okay, and this local max, or this relative maximum, you could not describe this as an absolute max, because, I mean, there's there's plenty of points on this graph that are higher than 1.32. Look at all of these and all of these, but next in our seemingly never-ending list of topics in this section, giant section, 1.2. Symmetry. The concept of symmetry, which is not a new word to you, I would imagine, but even functions and odd functions could be a new concept for you. So if you have a graph, and again, we're really just going to be looking at graphs to identify this kind of thing. So if we have a graph that is symmetric with respect to the y-axis, then we can identify that or label it, describe it as an even function. So that's a new terminology, a new term. An even function, when graphed, will look like it has symmetry with respect to the y-axis. And how, like, the y-axis would be like a mirror, you know, like the y-axis would be like an axis of symmetry kind of a thing. All right. Numerically, yeah, like you could show that numerically, or graphically, algebraically. I might, this might be worth highlighting, or I don't know, drilling down a little deeper with, considering what potential questions might be asked of you, especially on like a college board exam or something. But like, this is kind of how you might interpret it algebraically, but it really all goes hand in hand with, graphically what's going on with these even functions. There's also symmetry with respect to the x-axis. Okay? Not much to kind of elaborate on here. Numerically, you would see certain things in a table, if there was symmetry to the x-axis. Algebraically, graphs with this kind of symmetry are not even functions. They're not even functions, except the zero function. Y equals 0. But we can say that x comma negative y is on the graph whenever x, yeah. Lastly, we have symmetry with respect. What do you think is going to be here? Take a look at this example graph. You could say that this graph is symmetrical to what? There's symmetry with respect to the origin. Okay? Think about that for a couple seconds and it'll make sense to you, I'm sure. That a graph like this is symmetrical with respect to the origin, and that's where we get into the whole concept of a quote-unquote odd function. Okay? Odd functions. And especially if you have like the AP exam in your future, maybe it's worth it to you to kind of analyze this and make it a point to maybe highlight that, which is kind of the algebraical sort of description of odd functions. So actually answering questions for us here in the textbook and whatnot especially, and perhaps the only kind of question you'd be looking to answer on a college board exam. We're just going to graph them. So looking at this graph, which you probably shouldn't need Desmos to, like, you shouldn't like need Desmos or your graphing calculator to know what this graph was going to look like, and that it was going to be an even function. This next one, similar, I guess, but this is going to be neither. Is it odd, even, or neither? This is, neither symmetrical to the y-axis, nor is it symmetrical to the origin. So this is neither. This one, when you graph it, you go like, oh, that's symmetrical to the origin, so it's odd. Feel free to go back if you need to, pause, all that stuff. Because the next concept in this never-ending list of topics here is actually, it's like three at once. Continuity, asymptotes, which I've mentioned, and holes, which the whole thing about holes, well, same with asymptotes. They all kind of go together. So it's actually not three totally different concepts, like I said a few seconds ago. All of these kind of go hand in hand with continuity. Okay? But, so here we go. Continuity. Definitely a big term in calculus, so we're kind of getting into it here in AP Precalculus. A graph looking like this, you would say it's continuous at all x. Like it's totally continuous, meaning there's no jumps, there's no holes, there's no breaks. It's just flowing without any of that. Totally continuous with no interruptions of any kind. So the concept of continuity is not really all that tough to wrap your brain around. This, okay, is not continuous everywhere. Like it's not continuous at x equals a. So there's what we call a removable discontinuity at x equals a, whatever this is. Might get into more of that later, like what the heck this even means about it being removable, but for right now, just kind of getting the basics down. This next one, also a removable discontinuity. This is almost like the same graph, except this one's also defined up here at x equals a. They should have made this. I don't know why I just noticed this. But they should have made this like, if they're going to make this graph like kind of navy blue and stuff, like why not? Why make this point black? It's also a part of the graph. Anyway, I don't know. But whether it is also defined here, like flat out, this is not continuous at x equals a, and it's called a removable discontinuity. This one, you think this one's totally continuous everywhere? Heck no. This is not continuous at x equals a, but this one we call a jump discontinuity. And this one, okay, do you think this is continuous everywhere? It's continuous, but not across the entirety of the whole graph. So this one is what we could call an infinite discontinuity, because it looks like there's a vertical asymptote here. So that would be called an infinite discontinuity at x equals a, where there'd be a vertical asymptote. Moving on to some examples. Again, we're just going to be like looking at the graph, so not exactly Desmos, but when you look at this graph, you can kind of see how there looks like there is a vertical asymptote. So that would be an infinite discontinuity at x equals 2. Next one, how would you describe this? That's right, a removable discontinuity at x equals 2. Pause as needed. Just got to get through this video. I got to get through making this video. This is going to be a long one. Horizontal and vertical asymptotes. Okay. we've already seen these, and we've gotten maybe like a starting idea of what they are. A vertical asymptote is like this force field, kind of a thing, this invisible, even though we kind of usually draw like these dashed lines. It's technically an invisible force field on your graph that your graph will like approach on like an infinite sort of scale. Like over here, it's going to get closer and closer and closer and closer and closer, and then over here, same thing. It's going to get, on this other side, it's going to get closer and closer and closer and closer, like literally forever, but never, ever get there. So this part of the graph is actually heading to the right forever. Like it's never stopping going to the right. But in the same breath, it's never going to go as far to the right as x equals 2. At least not this part of it. And then over here, this chunk, it's going to go to the right forever. And this chunk is going to go to the left forever. But this chunk of the graph is going to be going left forever, but never as far left as this vertical line. So there's like, okay. Here we go. This is really fancy notation, which is what you'll be seeing again in calculus for sure. So this is like another big time sneak preview or early dose of calculus in your AP Precalculus course. And it's notation for what we call a limit. Okay? So this vertical line, remember, all vertical lines are y equals something. Y equals 3, or y equals -8, or y equals 2. This is literally the line x equals, wait, what are we doing here? Oh, this is horizontal. Sorry. There's also horizontal asymptotes, obviously, and that would be an equation for y equals, so maybe like move all these. Sorry about that, but obviously I caught my mistake pretty quick. X equals something would always be a vertical line, like x equals 3, or x equals -8, or x equals 2. So this is literally the line, the equation of this line is x equals 2. So that's what's going on here with this stuff. Y equals something is a horizontal line, x equals something is a vertical line, and we have this notation here about a limit. So let me just kind of focus on this one to help explain all this stuff. So the line x equals a, and here's a again right here, is a vertical asymptote if this is basically true, okay? We have a vertical asymptote if as x approaches, that's what this means here, as x approaches that vertical line, like that value, that x value, as we approach it from the left, that's what this negative sort of like superscript thing here means. As we approach that x value from the left, or from the right, as we approach it from the right, the function, like the y values, are approaching positive infinity or negative infinity. So looking back at this example right here, look, as the x values on my graph approach 2 from the left, x equals -3, x equals -2, x equals -1. This is where x equals 0. About right here is where x equals 1. As we approach, as the x values approach 2 from the left, the graph is approaching, it's going down forever. The values of the function are just blasting down towards, negative 100, negative 5,000, negative 20 million, like they're approaching negative infinity. Likewise over here, as we approach 2 from the right, as the x values get closer and closer to becoming, like they're never going to actually hit it, but as we approach 2 from the right, the values of the function, the y values, are blowing up to positive infinity. So that's what's going on here. Hopefully that makes some initial sense. A horizontal asymptote, we'll see this in action, I'm sure, here soon, but that's when, if you have x, going off to, like as x, as the graph goes off to the left forever, the function is approaching some value, and that would be like that horizontal line, that y value that it's approaching. Similarly over here, as x approaches positive infinity, or as we head off to the right forever, your graph would actually be like closing in on something, like a horizontal line, invisible line. Let's see this in action, like I just said. Oh geez. I feel like, well, okay. This could end up being a mix of identifying vertical asymptotes and stuff like that. This could end up being a mix of just looking at the graph or doing it analytically. You know what I mean? So without just cheating and looking at the graph, but so a vertical asymptote, right? If you recall from like earlier examples, it seems like forever ago, even in the same lesson, but where we'd have a vertical asymptote for values of x that are not in your domain. They're like illegal values that you'd not be allowed to plug in for x. So in this situation, if we take like an analytical algebraic approach, it'd be about factoring this guy in order to have a better view, like to see better how, like we would not be allowed to plug in -1 for x or 2 for x. So it's not going to be any surprise when we look at the graph that we see those vertical asymptotes there. And also, doing a little bit of numerical algebraic analysis of this equation, it shouldn't be any surprise if you take a graphical approach and you look at this and go, yeah, it looks like there's a horizontal asymptote of y equals 0. And notice how, as the graph heads off to the left forever, as x approaches negative infinity, you see how the graph is approaching a y value of 0. Likewise over here, same thing, but as we approach it, as x goes off to positive infinity, off to the right forever, the graph is getting closer and closer and closer. It's approaching y equals 0. End behavior. Horizontal asymptote gives one kind of end behavior for a function because it shows how the function behaves as it goes off towards either end of the x-axis, to the right or left forever. Not all graphs approach lines, but think about a parabola, for example. A parabola, like a normal, regular, like the parent parabola, wouldn't that end behavior go up forever as we go off to the right forever? And on the other side, wouldn't it be going just up forever again as we also head to the left forever? So, some examples here as we really near the end of this really long lesson. This could be a 3-day in class, by the way. at least 2 days of class to get through this monster. But, So, match the functions with the correct graph by considering end behavior. Okay. Now I'm taking maybe I'm taking a backwards approach here, but to help you understand. Okay, ready? So end behavior is all about as we think about like what happens as x just gets bigger and bigger and bigger and bigger and bigger, literally approaching infinity. Okay? Or, as x also approaches negative infinity. So this one is D, okay? Because think about it. Up top, and I don't know if you want to make little written notes about this, like some of the things I might say here over the next couple minutes. But in this equation D, the top is 3x to the fourth power. The fourth power, okay? And by the way, it's an even power. Compared to the bottom, if you let x just like blow up, like you're plugging in like 100 for x up here and 100 for x down here, 1,000, 1,000,000, okay? The top is blowing up a whole lot faster and a lot more strong than the bottom. So as x heads off to the right forever, it's just blowing up, okay? But also if we plug in like negative 1,000, negative 1,000,000, negative billion, trillion, okay? Even though we're plugging in like negative numbers, if we're raising it to the fourth power up here and the second power down here, it still ends up being like a really, really, really big number up top, but positive, divided by a really, really big number on the bottom, just not as big as up top, and also positive. So it's blowing up to positive infinity as x goes off to negative. I know it's a lot to think about maybe at first here, but I think with practice and maybe a little more thought, you can kind of make sense of that. Example C, or equation C. Once again, the top is winning. Like the numerator is blowing up a whole lot faster and a whole lot stronger than the bottom as we plug in like really, really big numbers. If the numbers we're plugging in are like positive, like positive 1,000,000, positive 1,000,000,000, okay, the top's going to be positive and the bottom's going to be positive. So we have like a positive answer overall. But as we plug in like negative, as we let x go off to negative infinity, the top, because it's an odd power, the top is going to be really, 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 really big, but negative. And the bottom is going to be, big, but not as big, but positive. So we have like a negative divided by a what's a negative divided by a positive? Negative. So as we go to the left forever, we're actually going down forever. This one, okay. Long story short, x squared over x squared, it's kind of a tie, So as numbers get really, 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 really big, okay, it's almost like, like what's 3 million divided by 1 million, Well, 3, but like then what's 3 trillion divided by 1 trillion squared, or 1 million squared, 3 times 1 million squared divided by 1 million squared, 3 times 1 trillion squared. So when it's a tie in the powers, the answer here is B, because as we plug in like really big numbers, it's going to approach equaling 3, because it really just boils down to 3 divided by 1, this plus 1 does not matter at all. Okay? So that's why you can tell, like, as x gets really big, the graph is just sort of zeroing in on this horizontal asymptote of 3. See, like 3 right here, this horizontal line. Same thing if we're plugging in negative numbers, because if we square a negative number and square it's still going to be the same positive number divided by a positive number. So we're also approaching positive 3 as we're going off to negative infinity with our x's. And example A, look, now for once, the denominator is blowing up faster because it's x squared, and this is just x. So what do you think happens? What do you think this whole fraction approaches? This whole thing, the whole enchilada, is approaching if the denominator is getting bigger and bigger and bigger and bigger, and it's growing way faster and way stronger than the numerator is approaching. Like, think of it this way, just as a comparison, 1/2 becomes, 2/5 becomes 3/10 becomes 4/100 becomes 5/1,000, becomes 6/1,000,000. Like, what's that whole fraction approaching? 0. So look at the graph. As x blows up to infinity, like as we plug in numbers, positive numbers for x, we're still approaching 0, but from above. Because you'll have like positive numbers that are approaching 0. So that's why, like, the graph is above the x-axis, but as we get closer and closer and closer to the x-axis. But if we're plugging in negative numbers, okay, that means the top is negative, and the bottom will be positive and a lot bigger. So, like, we're still approaching 0, but now all the values, if you were to make a table, they'd be negative, but still approaching 0. So that's why this one's approaching 0 from underneath, and constantly negative values, but still approaching 0. Okay, so that brings us finally to the end of this section, this video, which, again, at least 2 classes worth of time here, maybe even 3. But thank you for your attention and your effort, and that's it.